Okay, welcome back, guys. We are going to jump right on back into functions. And the goal of this lesson is to really look back at linear equations and sort of understand how they really are just functions, okay? So we're going to learn a new term today, but when we break it down, it really isn't that new, okay? So we're just going to learn about the idea of a linear function, okay? And well, what is a linear function? Well, if your mind is jumping back to a linear equation, that's perfect because that's essentially where we're going to go with this. But let's sort of break it down. So, if you remember, a function, okay, we said was a rule that assigns to each input value exactly one output. Okay, so that's just a regular function. Well, a linear function is just, well, it's a function, but the specific rule that assigns to each input value exactly one output value, that rule is just a linear equation. A function is called a linear function if it can be described by a linear equation. What does that mean, described by? Well, it just means that, so let's look at our little machine picture of a function, okay? So we said we take in inputs, which we usually call x values, and it spits out outputs, which we usually call our y values, okay? And for a function to be described by a linear equation, all that means is that the rule which these inputs follow, if that is a linear equation, then you have a linear function. So let's just look at, so let's put a linear equation in here. Let's come up with one. So remember, linear equations look like y equals mx plus b. Okay, so I'll just pick, let's say m equals 2 and b equals 1. Okay, so our linear equation would be 2x plus 1. Okay, so from that, then we can set up our list of inputs. So that's just x, and outputs, so our y. Okay, and sort of draw a table here. And let's see what we get. Let's plug in 0 for x. Well, we get 2 times 0, which is 0, plus 1. 0 plus 1 is just 1, so for our output we get 1. Let's pick 1. Okay, 2 times 1 is 2, plus 1 is 3. Okay. Whatever, just keep it consistent. Let's try 2. Okay, 2 times 2 is 4, plus 1 is 5. Okay. So we could check, there are ways to check if this is linear, but we know it's linear because we made it to be. We followed the slope-intercept form of a linear equation. So this now is a function that is described by a linear equation. Okay? And if you guys remember from like an earlier video, I was talking about sort of the distinguishing between function and equation, and how I would probably just use the two terms interchangeably, which is not 100% correct, but it's correct enough for us to use. Okay, so let's jump on into this first example. It gives us this list of values, this sort of data set, okay? And we need to figure out if this is a linear function. So we have two rows. Our first row are x values, so those are going to be our inputs, okay? And the second row is our y values, and those are going to be our outputs, okay? In order to find out if this is a linear function, well, we need to know two things. First off, we need to know it's a function. because if it's not a function, it certainly can't be a linear function. And once we are sure it's a function, then we need to figure out if it's linear. Just meaning, if it's described by a linear equation, like what we just talked about. So first, let's check if it's a function. Okay. So remember, the definition of a function is a rule that assigns to each input value exactly one output value. Okay. So does each input have an output? Yeah, it looks like it does, because every number in the input row has an associated output value with it. Okay. So we're good there, but we need to make sure that there is only one output for each input. So none of the x values should repeat. Okay, and it doesn't look like they do. We've got 1, 2, 3, 4, 5, 6, 7, and 8. So none of them are the same, so that's fine. But just to show you kind of, guys, what it would look like for that rule to be broken is if we had, say, another column over here, and let me just pick a number that's already there. Let's just say 4, okay? And if there was a 4 here, and then it had something like 12, right? Well, the output for 4 can't be both 5 and 12. You got to get the same answer every time you put 4 into this function machine. You got to get the same thing. So if this were the actual data set, this would not be a function because you've got an input up here, the input 4, that has 2 different outputs, and that can't happen in function land. But we don't have that, so we are good to go. So we do, this is a function. This data set does give us a function, and now we just have to figure out if that function is described by a linear equation. Now, to figure out if a particular data set is linear or not, well, we luckily we have a bunch of tools in our toolbox to do this. Okay, so let's just start at the beginning. So way back, we learned about proportions. Early 8th grade and sort of back in 7th grade, you learned about proportions and what we call the constant of proportionality. Okay, and that was this equation right here. You guys saw y equals k times x. Okay, and we said that k value was your constant of proportionality. Okay, well, now looking back on this equation with your newfound linear equation tools that you've put into your math toolbox, hopefully you guys notice that this looks a lot like some of the things that we've been working with. And in particular, what I'm throwing out there is this y equals mx plus b that we've seen so much of lately. Okay, so this is sort of the slope-intercept form of a linear equation. So it gives you the slope of the line if you graph it and the y-intercept on the graph. Okay, and you say, well, the equations kind of look similar, like they both have a y and they both have an x, but I mean that's about it. Well, what we are mostly concerned with is that we do have a y and an x. We've got something times the x. There's some number, some constant. Remember, values in your equations that don't change, they're not the variables, those are called constants. And so even though these are letters right now, when we actually fill in the equation, there's going to be numbers there. Y and x are your only variables in the equation, so those are the only ones that are going to stay y and x. But so how do these two equations relate? Well, I argue that this equation is just this equation, but we just have, so our slope is now that value k. So another word for the constant of proportionality is just slope. Okay, and Well, where's the y-intercept? Where's the b in this one? Well, b is just equal to 0, okay? And what that means is the y-intercept is at the value x equals 0. So when y equals 0, x equals 0. And hopefully that makes sense to you guys with this example. I'm just going to add a column here. Because how much money would you have to pay if you bought 0 bags of candy? Well, hopefully you all answered $0 if you buy 0 bags of candy, because you're not getting anything. And that should also make sense, because one of the main things about proportions was finding out if an equation was a proportion. We had to figure out if it went through the origin, okay? And having a y-intercept of 0 in a linear equation, that means you go through the origin. So since it goes through the origin, if this equation is linear, then it's going to look like this, and all we have to do is figure out that constant of proportionality, and then we have our equation. Okay, let's just assume that it is linear. Okay, we don't know that it is yet, but let's just assume that it is. So that means it's got to look like this. It's got to look like this, or at least looks like something that we can make look like this. So we already said it goes through the origin. So its y-intercept is 0. So we know that it's this so far. So solving for k, that if we solve for the constant of proportionality, that will give us the slope. So remember, the constant of proportionality, right, was another word for constant of proportionality was the unit rate. So if we sort of solve for k in this equation, right? Oops, it was y over x. Okay, we divide by x on both sides. The unit rate was whatever. So it was something over 1, right? So it was whatever the y value was when x was equal to 1. That was the unit rate. And in this one, it looks like 1.25. Okay, so if this is in fact linear and a proportion, it should follow. So we said k is equal to 1.25, so y equals 1.25x. Well, it should follow that, but that's kind of assuming a lot. So another way that we could figure it out is, remember the slope formula. So we said m is equal to remember this triangle, so it was delta, and delta just meant change. So the change in y over the change in x, right? And so we picked y. Some y value minus another y value, and then the x value attached to that first y value minus that x value attached to that y value. Okay. So if we do this as an example, let me just pick, so my pair x2, y2, that's going to be this column here, and x1, y1, I'll just pick u here. Okay. So the y value from our second column, the y value is 10. The y value from the first one is 5. And the x value from the second one was 8. And the x value from the first one was 4. Okay. 10 minus 5 is 5. 8 minus 4 is 4. So we get 5/4. Okay? So that says that this should be, well, when we already know, so this should be y equals 5/4 x plus b, but we already know b is 0, so you just leave it at that. This is looking good because fourths are kind of easy to deal with, because you can just think of like $1 in quarters. And, quarters 25 cents, and there's 4 of them that make up $1, okay? So when we're taking things out of 4, we can kind of just use that. So you can think of this as, I have 5 quarters. Well, how much is that? Well, that's $1.25. And 5 quarters is, in fact, 1.25. Okay, so this is a good sign that when we solved it using the unit rate and then we solved it using the slope formula, we got the same answer. So that's a pretty good sign that this is the right equation. Okay, and these are the same thing. So what I want you guys to do now is go through this table, and I want you to fill in the values for x and y and see if they are true for all of the values that are in this table, 1 through 8, okay? And then I want you guys to go ahead and graph this guy. So draw out a coordinate plane, label your axes, and plot all of these pair values here, these coordinate points. Plot them on your coordinate plane and make sure that you get a line. Once you finish that, I want you to give example 3 a try. Okay, so it says Veronica runs at a constant speed. The distance she runs is a function of the time she spends running. The function has the table of values below. Okay, so really you're going to do this one kind of just like we did the last one. Just like we had in the last one, got this table of values, and it looks like our inputs are time this time instead of bags of candy, and our output is going to be a distance, so miles that Veronica runs. Okay, so think about what it means for Veronica to run at a constant speed. And then what I want you guys to do for this one is try and find, so use a proportion or the slope formula. You should be able to use that based on some of the clues in here. So use those things to write the equation that describes this function, the function in this table here. Okay. Then go through each of the values in the table and verify that your equation is the right one by making sure that all of the inputs give you the correct outputs. And the last thing I want you guys to do is graph this guy.